again, I just kind of want to point out this notion of looking at the regional impact of one restoration area and how it interacts with the channels in its neighborhood, I think is a very, very interesting upcoming concept.
Let me just move on to the last slide then. So our recommendations are the board might consider having procedures that increase the demonstrable quality and discussion of modeling results and conclusions, both at the board proceedings and before the board proceedings. Improve the organization and coherence of modeling work and insights, particularly through encouraging there to be technical plans for the development and use of these models by different state agencies in particular. Along those same lines, improve the long-term development and analytical tools and data among many groups. And then I think finally, this is part of the dialogue, I think, between science and policy, is we often try to organize science to be better for policymaking, but I think after having been involved in several forums of policymaking in California, sometimes the policymaking forums need to be reconfigured so that they can better employ modeling results in science as well. So I think it's like as with any dialogue, you have to listen and you have to hear and you have to talk as well, so on both sides. So thank you very much for your attention. I'm sorry that we ran over a little bit.
I'm glad you ran over. That was interesting.
If you have more questions, you know where we live.
As long as you don't know where I live, we're okay. Thank you very much. We're going to take 5 or 10.
No, hang on. We do have a very brief, thank you very much, you guys. We have a very brief statement from Elaine Archibald, and then we'll take our 10-minute break.
Okay.
So go ahead. And Elaine, can you introduce yourself? And your microphone's on, I think.
Yes. I'm Elaine Archibald, and I am the Executive Director of the California Water and Environmental Modeling Forum. And I've been given less than 2 minutes to speak today, but my main message is that we are here to assist you with this process. We understand the challenges that you're facing, and our forum is a nonprofit, nonpartisan, collaborative organization that is highly respected within the state of California. And in fact, many of the people sitting in this room today are members of QEMP, or they have been associated with QEMP at some point in the past. And we can help in several ways. First of all, our organization conducts technical workshops. We could assist you by bringing together some of the fisheries biologists with some of the hydrodynamic modelers to start to answer some of these questions that have been brought up in the panel today. We also conduct independent and impartial model peer reviews. We are currently working on a groundwater model peer review. And in our peer reviews, we bring in impartial experts to assess the strengths and weaknesses of models, recommend improvements to the models, and also talk about what the proper application of various models is. And similar to the community-based modeling approach that's been called for today, back in 2005, QEMP called for development of a strategic analysis framework. And in that document, we called for a framework in which we could start developing the databases that would then be able to be used successfully with the models so that we could answer questions and potentially solve some of California's water-related problems. So that document could actually be the basis for the beginnings of a Delta modeling plan that could be developed in the next several months to a year. So we're here to help. We're happy to talk further with you and with your staff, and we hope you take us up on this offer. Thank you.
Thank you, Elaine. We'll take a 10-minute break and resume at like 5 after. Thank you.
Peter.
I don't want to hit my coffee or my iPhone. Ladies and gentlemen, as much as I like to see congeniality in this room, which is in short supply at times, we need to get going again here, or Dr. Bernstein is going to zap me with something. You only have the luxury of ignoring me for just a second. Please have a seat. Believe me, at times congeniality and adult conversations are in short supply in this room. I hate to cut it off, but we need to get going. Russ, are you the first one or David?
I am the first one.
We have a standing rule here. The better the education, the more difficult it is to turn on the microphone. That's why mine's always on. Please.
My name is Russ Brown. I work with ICF International, and I'm part of your consultant team on the Bay Delta Plan review and possible revision. And I wanted to introduce a couple of basic ideas into this mix of analytical tools. My main point today is simply that we should collectively look at all of our data more. We should evaluate and learn from the daily historical data of both water and fish. So many of us in the room, and you may be most familiar with what I'll call water accounting, tracking the flow of water from rainfall to runoff through our reservoirs, in our diversions, into the delta, into exports, or into the estuary. I'm wanting to suggest that if we tracked this using all of our daily data, this would give us a much more clear picture of what actually has happened in the recent years. And each year has lessons to tell us. I'm also introducing the idea that we could be doing fish tracking in the same way. Daily fish data, tracking a population from its spawning, egg incubation, rearing, migration, movements up into the delta, through the delta channels, as John was showing us, and do the same type of accounting for fish. We were asking ourselves just earlier, what are we looking for? And I'm suggesting that what we'd be looking for in collectively reviewing the historic available daily data is we're looking for relationships between flow and fish, or one of the intermediate relationships between flow and habitat conditions, such as salinity, which John also was showing us, or temperature below the upstream reservoirs, or turbidity. And as we discover or become just better aware of these relationships, this then allows us to evaluate what happened and what were the major causes, thinking of flow as the cause that we are trying to really focus in on, to other things that happened in the estuary or in the upstream rivers. So I have a short time with you, and I'm wanting to just show you what this might look like. So I'm doing one of my favorite things, which is showing you my graphs. And my graphs are almost always a time series of daily information. And I have 4 examples that I hope to quickly move through. And I hope that some in the audience have picked up my handout, which is sort of data cartoons that you could look at, kind of like instead of reading the paper, and just get a feeling for what I'm talking about. I'm thinking that we should be doing a lot more of this, and if we did, we would learn a lot more about the system that we're trying to manage. So let's just jump right in. So these are graphs, and of course I'm not expecting you to remember these graphs exactly, but just get a feeling for what I am talking about. So here are 2 graphs for water year 99. And in the top graph, I have quite a few of the delta flows, which are solid lines. Like the red graph is the exports, and I have positive exports going to the top, even though it's negatively labeled, because the blue line, which is the one I want you to just kind of look at for a second here, is the Old and Middle River flow. And halfway down the graph is the 0 line on the right-hand scale. And so the Old Mill River flow responds to exports, but as John was showing us, it also responds to the San Joaquin inflow or to the flow coming from the Sacramento down the cross channel. So it has sort of positive and negative influences, and it wiggles around. But I'm not trying to get you to remember all that. I'm just wanting you to see that I'm also plotting on this graph daily fish data. In this case, I'm graphing the daily salvage at the CBP and the state export facilities at their fish protection facilities. And these daily dots or triangles, green for the CBP, red for the state project, has a particular pattern to it. And if we had more time, we'd realize, or we could sort of explore together, that the adults are showing up in December, January, February, March. And this year, predominantly, there was a migration of adults into the South Delta in February. And they showed up at the pumps. And then 3 months later, in May, there was quite a large salvage event of the small fish, the juveniles, the 1-inch fish. And somehow, we're all looking for what was the relationship between the flows and exports in the South Delta and maybe other places and these fish movement patterns. In the bottom graph, I'm simply showing the same fish data, but this time with the delta outflow. So a lot of people in the room have a conceptual model that the adult delta smelt moves somehow in response to one of the first or a major outflow event. Not shown on this graph, but what we would show if you were to endorse and sort of mandate that this kind of data collection be done would be the turbidity patterns that occurred in the delta that may also have something to do with the fish. So that's an idea of where you can bring daily flows and daily fish together, and I'm saying that there's much more of this that could be done. So now in this graph I'm showing you, this is what I call day flow illustrated. You may realize that as a part of the D6, or back in '78, your initial D1485 decision, the beginning of IEP, a data set was prepared annually and still is, showing what the daily flows in the delta are. And I'm suggesting that you ask that this day flow be expanded to include day fish and day salt and day temperature and day turbidity and day anything that any of the rest of us measure or know about, and that we all have this shared data set, and then I'm adding to that some graphics or some illustrations so that we can begin to compare the variables. Again, you're not going to be able to remember all of this, but in the top graph I have the Sacramento River inflow, in this case for water year 2008. So 5 years ago, the first year when OMR limits were invoked by Judge Wenger. And what I'm showing is the historic cross-channel opening and closing. And the way I've shown it here is they're the two light blue lines. The top line would be the flow that would be diverted off the Sacramento if cross-channel was open. The bottom is the flow that would be diverted through Georgiana Slough if the cross-channel was closed. And in this case, since there was fairly low inflow, in the summer period, just 10 to 15,000 coming in on the Sacramento, the cross-channel closure blocked about 2,500 CFS of flow and fish from entering the central delta. And all I'm wanting to say in our little example is, are we sure that closing the cross-channel is what we want to do each day? And I just raised that question. It's a hypothetical question, but I'm saying closing the cross-channel does more than simply block Sacramento water from entering the central delta. It also blocks the fish. That's why we normally close it. But it is changing the flow in the San Joaquin River on the top of Frank's track, if you remember John's illustrations, going down past Antioch, the outflow from the San Joaquin, which in day flow is called Q West, the cross-channel closure reduces Q West and causes Q West to often be negative. I'm not saying what that might be doing to estuary fish who are in the confluence region, but the idea is that when we close the cross-channel, we're doing more than just closing that gate. We're actually changing net flows throughout some of the rest of the delta. On the bottom graph, I'm just illustrating that the San Joaquin inflow could be compared to Old River, could be compared to the exports to consider where the fish that are in the San Joaquin flow are ending up. Okay, I'm going to just skip these graphs, but we're looking at other, or try to go quickly here because I'm out of time. One of the main things that we can now do if we had all the daily data like day flow but expanded to other parameters all available is we could simply change some of the choices that we made. Like we could open or close the cross channel, do the opposite, see how that change flows. In the top graph, I'm illustrating what actually happened in 2008 when the OMR limits were imposed. The dark blue is the OMR without the OMR limits. The light blue is the required OMR, that it not be less than 5,000 in a negative sense, or whatever they controlled it to. Maybe, I can't quite read it either, 4,500, let's say. So they limited OMR to that. They had to reduce exports to get OMR to be limited. And changing exports changed the outflow as well as the exports. It changed QS. So even the few parameters that we do change within the delta have repercussions other places. And I'm saying the daily historic data is the most accurate way to begin thinking about what will happen. Okay, I'm totally out of time. So I'm going to skip to the end. The idea of sort of illustrating day flow and adding to day flow with all the other parameters is my basic recommendation to you. And I am suggesting that you could request this in the same way that you have requested day flow, that the agencies who run the delta would report back with an official tally of all of the measurements that are in the delta. The fish agencies would report in with the same daily data. At the bottom of my presentation, there are just the 4 basic reasons that I think that we should do this immediately. It gets us started on the grand plan that the panel introduced, that we should have a coordinated modeling team. Well, let's start with the simple daily data from all data types brought together in a simple framework so that everyone could have it. That allows you to check and see whether your rules were obeyed. If your rules were obeyed but there were still problems, this helps us identify where we should change the rules. And then I'm saying it's the beginning of an impact analysis or an effects analysis by comparing 2 cases, starting with the historic data as our baseline and making adjustments and doing an analysis that way. Well, thank you.
While the slides are going up, I'll introduce myself. I'm David Perkey. I manage the U.S. Water Group within the Stockholm Environment Institute. I'd like to thank the board for this opportunity to present our modeling platform to you as a possible tool that you might consider useful in your deliberations. I'd also like to thank the panel for a very insightful and interesting conversation. They made a lot of points which I will try to incorporate into what I'm going to say this morning. And I'd also like to thank the staff at the State Board for giving me the opportunity to make this presentation. They saw this sweep model in various other forums and thought that it might be of some use to the process that you are undertaking and invited me to present this model. So let me just introduce briefly WEEP, the Water Evaluation and Planning System. This is a generic, object-oriented, programmable, integrated water resources modeling platform that we've been developing within the Stockholm Environment Institute for approximately 20 years. And I'll start with just some why WEEP statements, and then hopefully as I present the application here in the Central Valley, these might be justified. WEEP is modern modeling software. It's not a modeling code, it's a piece of software. We have a global user community of over 10,000 registered users. We continually upgrade and improve the software based on the efforts of a team of software engineers that we have within the Institute. WEEP is free to all entities of California government based on our relationship that we've developed with the Department of Water Resources. WEEP includes no dependencies on historical time series, which I think is an important thing to consider as you think about how to think about the future. We've built this model so it's not running based on historical time series data. It integrates a lot of the issues of concern: water flows, hydrology, system operations, environmental flow regulations, water quality, finances, and economics. It's been constructed intentionally to support scenario analysis. So its best use is when you run the model under lots of different assumptions about the future and understand the implications of different choices and different uncertainties. And WEAP is used currently for two major system-level planning exercises. One is the State Water Plan Update process within the department, and the other is the upcoming basin study that's going to be managed by the USBR. And it was the application of WEAP to these two studies which caught the attention of the technical staff here within the state board. So here are some functionalities that WEAP has that I think might be of interest to you. It has internal snow accumulation and snowmelt hydrology built into it. It does rainfall runoff modeling, so it's modeling the hydrologic system, and that includes a detailed representation of evapotranspiration from both natural and cropped landscapes under different climate regimes in the future. It has soil moisture storage routines, which allow you to estimate evolutions of crop water demands and crop yields. It has groundwater representation that includes dynamic modeling of stream aquifer interactions. It allows for the modeling of the operation of hydraulic systems, including hydropower. There's models which allow you to represent different patterns of urban water demand. It represents different water allocation priorities that have to be made in times of scarcity, including environmental flows. It has surface water quality routines and also embedded financial and accounting routines to do cost-benefit analysis. I think the implication of this slide is that WEAP is attempting to be an integrated modeling software where a lot of different pieces of analysis are pulled together into a consistent platform. So this is a screen capture of the WEAP application that we've built for the Department of Water Resources and the U.S. Bureau of Reclamation. These are the WEAP objects in this object-oriented framework. You probably can't see them, but we have reservoirs and rivers and groundwater and demand sites and watersheds and treatment plants and canals and the like. Jay Lund made the point that models are only as good as their modeler, and so here I'd like to take the opportunity to thank Brian Joyce, who actually did most of the work in developing this application, a fantastic modeler. And Jay also said that any good modeler would talk about the weaknesses of their models as well as the strengths. So I thought I would mention some of the things that I think could be improved in this tool. It has an incomplete representation of all the details of project operations. It's meant to be more of a high-level system representation and doesn't get into some of the fine details of the allocation logic for the projects. It uses priorities rather than always economic considerations for allocating water between various uses in times of scarcity. It has a monthly time step. Some of the analyses that people want to do might be shorter time steps. And the run time for applications this complex can be a bit long and could be improved. So there are some weaknesses. There's many others. But now let me just tell you a little bit about the strengths of this tool. First of all, let me talk about its evolution. We started building this application for the Sacramento Valley in 2005 with EPA funding. Then we moved it to the West Sacramento, San Joaquin with CEC funding, and then to the entire San Joaquin with DWR funding, and then built the Tulare Lake Basin with USBR funding. And the model actually includes representation of 25 rim watersheds where we're able to simulate hydrologic processes under different climate regimes, different snow accumulation and snowmelt regimes, and different watershed yield regimes in the rim watersheds. And then we also represent 21 planning areas on the valley floor where we're looking at the demands separated by irrigated agriculture, outdoor urban use, indoor urban use, and managed wetlands, 22-inch stream flow requirements, 21 groundwater basins, and the exports to the coastal demand areas. We've done a long series of calibration on this model, looking at various things like the reservoir inflows, reservoir storage, demands, groundwater use and groundwater elevations, and delta outflows and exports. So here's just some examples of output from these calibration exercises where we were trying to compare the simulated and observed values in various domains and various dimensions. This is the simulated outdoor urban demand as driven by climate data in the Sacramento and the San Joaquin valleys for different planning areas, Sacramento on top. This is a comparison of the simulated and modeled reservoir storage in the Sacramento Basin for several of the important reservoirs. Not perfect, but Again, capturing the basic behavior of the system. This is our calibration for the delta outflow that we're simulating for this historical period. And this is our calibration of the simulated net evolution of groundwater levels in various parts of the Central Valley. The red being the simulated groundwater level and the gray being an aggregate of several different DWR monitoring wells. So having calibrated this model with DWR, we're integrating it into a scenario analysis where we're looking at different uncertainties about the future, climate, demography, land use change. We're evaluating different response strategies related to efficiencies and wastewater reuse. We're running those combinations of uncertainties and response strategies through this WEAP application and then looking at certain metrics of reliability. Oops. And then looking at designing response packages that we can look at how they perform in terms of improving the performance of the system relative to the base case. And keep an eye here. The results I'll show you are for 3, where we're improving the urban water efficiency, doing some groundwater recharge, and a lot of water recycling. And you can see these are for all these different combinations of future climate and demographic future conditions, uncertainties. The starting point for all these is with the base case in terms of the urban water reliability and the agricultural water reliability. And as you implement these management responses, you can see, you can develop graphics that kind of show how the system performance changes under different management futures. Just a couple of mentions of other applications that we've built for other parts of California. The list is here. We've done some of these for research, some of these in collaboration with utilities, some of them for IRWMPs. We've published a lot of papers on these various applications. So again, why WEAP? It's modern software. It's not a site-specific code. We have a global user community, not just a small number of proficient users. We continuously upgrade this software. It's with software engineers. It's free. You don't need any expensive solvers to run it. It doesn't include any dependencies on historical time flows. It's not restricted to the period of record hydrology. It integrates the concerns across, many of the issues of concern across a consistent platform. It's not an assemblage of otherwise disconnected models. And it has been constructed for scenario analysis. It does not require extensive coding to represent new management arrangements. Thank you very much.
I have one question. So do you see this being used in conjunction with some of the modeling that was being discussed by the science panel? I mean, this would be more, as you say, much higher level scenario exploration that might then send you back to some of the more detailed work.
Yeah, I haven't spoken with the state board staff about their interest or their potential interest in using this tool, but in detail. But I think one of the things that they were considering was using this platform to do some early exploration of sort of larger scale opportunities and larger scale changes in the way the system is regulated and operated, to begin to sort of find the sweet spot of where there might be some arrangements that can achieve multiple benefits. And then perhaps taking some of those strategies and some of those scenarios about the future and then running them through, the more classic regulatory models that have been used in the past. That's one option, certainly.
Thank you.
I might as well ask, while you're both here, we heard the importance of looking at processes and biology on a daily time scale from the first presenter, and then we had an acknowledgement of the weakness of the WEAP model was as a monthly time step. This was something that's sort of hovering in the background of the invited panels report that I read. The importance of time scale. Ken, maybe to give you a question, are there opportunities within the WEAP framework to drill down and have a more fine time scale in the running of scenarios, or is it just too big?
Yeah, the software itself is open, that allows the user to define the time scale that's used in the model. And we chose a monthly time scale for this application because it was being used primarily to support these planning studies. We have done other applications in California, for example in Butte Creek, where we ran the model at much finer time scales to look at the interaction between water temperature, hydropower operations, and salmon life cycle, salmon survival. And so there are opportunities, I think, to drill down into much more focused areas where you might have some specific concerns about these interactions. But at this large system level, for this planning purpose, the monthly time step was the appropriate one. And to rebuild it for a daily time step at that scale means the model has to be sort of rebuilt and recalibrated. So.
Can we have our regulatory and fisheries agency panel come up? I wish we had somebody coming up that I didn't want to listen to so I could get back on schedule, but I don't know how I'm going to do that, so. What's that? Well, I could skip lunch, I can tell you, after being away for 10 days. My crib sheet doesn't tell me who the self-moderator is, so someone's going to take the lead. If we don't, I know Bruce will want to. No offense, I just wanted to make sure you were awake.
Good morning. Good morning, Chairman Hoppin and board members. We have a variety of members from the state and federal resource agencies here. Then I think I'll just let each person identify who they are. My name is Dean Marston. I'm a program manager with the California Department of Fish and Game.
These microphones came with my great-grandparents across the plains in a wagon, so you have to really center up on them. I'm sorry.
Okay, my name is Robert Hughes. I'm a hydraulic engineer with the Department of Fish and Game.
I'm Pat Colston. I'm a staff environmental scientist with the Department of Fish and Game's Water Branch here in Sacramento.
I'm Julie Zimmerman. I'm a biologist with the Fish and Wildlife Service.
Bruce Herbold, the fish biologist with the Environmental Protection Agency.
I'm John Don Soikon. I'm a ecologist with the National Marine Fisheries Service in Santa Cruz.
I think that's everyone. So I've been asked to.
Dean, that, yeah, if you put it, yeah, that'll work. I don't know. It's kind of like hot air doesn't rise in this building, so you got to be right on it.
Keep it low. We're good. All right. So I've been asked to start off here on the presentation. So again, I've been asked to give an update to the board on SWRCB, otherwise known as the Salmon River Fall Run Chinook Salmon Population Model. And I'll state up front that this is a superficial overview because it would take literally hours to dive down in the weeds of all the things that SWRCB can do and the questions it can address. So the best I can do is give you a superficial overview in the few minutes that I've been allocated. It's a collaborative effort between state and federal resource agencies as well as academia and private consultants. And by way of overview, I just want to turn our attention back in time that the department was asked to address a specific water quality standard. In other words, the standard in question dictates the models needed. If flow, then use a model of flow if the standard is flow that's being evaluated. There's been several model versions. The most recent that's on the street is model version 1.6, and this model directly addresses the Salmon River South Delta inflow question. Version 2.0, aka SWRCB, also addresses South Delta, Salmon River, and trib flow questions, as well as addressing multi-ecosystem questions. So why SWRCB? For one, it's been peer-reviewed. Two, it will be suitable for management use. It's completely transparent. When I mean transparent, that means all the model will be completely documented in its report, which will be out here shortly. All the model computations will be transparent so people can see that it's correctly computing for itself. All the variables that are in the model and all the assumptions and some indication about the confidence intervals with respect to results that the model produces will be included in the documentation to ensure transparency. Again, well documented. It's based on best available science and has been developed using well-established scientific procedures and protocols. So what is SWRCB? It's a full salmon life cycle model. Estimates survival, movement, and/or development in 3 ecosystems. includes a variety of factors that we've heard discussed earlier this morning, like in-stream flow, water temperature, predator abundance, harvest, exports, carrying capacity, hatchery, floodplain inundation, ocean conditions. It actually includes also water operations and a resulting water temperature response model within SWRCB as well. So it has water operations, water temperature, and fish production. And determines fish production at each life stage, juvenile back to adult. And includes both the Salmon River main stem as well as tributaries in the San Joaquin, Merced, Tuolumne, and Stanislaus rivers. So here's a geographic footprint of SWRCB. And we have inland component or ecosystem, a delta ecosystem, and an ocean ecosystem. So I'll start with inland ecosystem. So using New Melones as an example for the Stanislaus, SWRCB will encapsulate New Melones Reservoir, the lower Stanislaus, all the way to the confluence. If I can get the mouse to work, we'll be doing good. With the San Joaquin. For the Tuolumne, New Don Pedro Reservoir complex, lower Tuolumne, the confluence with the San Joaquin. Merced, Lake McClure complex, and the lower Merced to the confluence with the San Joaquin, as well as the Millerton Reservoir complex and the lower San Joaquin River from Friant, all the way downstream to Mossdale. Then we enter the delta ecosystem, and this has the points of going from Mossdale on the inlet side of the South Delta to Chips Island, which is the exit from the delta into the bay and ocean ecosystem. And the ocean ecosystem extends from Morro Bay to the south to the Oregon border to the north, which is where the majority of Central Valley produced salmon are caught off the Pacific coast. SWRCB, with respect to the salmon production part of it, actually has 8 modules, ranging from inland module all over to the spawning module, and we'll take a quick glance at these. So for the inland module, I'll just use Stanislaus by way of example. So it starts with eggs being deposited in redds in the spawning reach, the lower 20 most mile reach here. And as a function of water temperature, will actually develop eggs, cause them to hatch, and then grow into fry, par, smolt-sized fish, and then out-migrate the Stanislaus into the main stem San Joaquin. You can see here some of the survival and development factors as well as movement factors that the model incorporates. So once the juvenile salmon enter the main stem San Joaquin, then we need to route them into the South Delta and also account for their survival and development as the fish are moving downstream into the South Delta. Once they enter the South Delta, then we want to estimate their survival if they're smolts, or development if they enter the South Delta as fry or par. And some of the survival factors here that we've looked at are water temperature, inflow to the delta, water export, striped bass abundance, as well as the head over barrier status by day. And I'll say that the SWRCB inland module is a daily time step, and the previous module is a daily time step, and the delta module is a daily time step. Now we move to the ocean. So this is an annual time step, and as the juveniles enter the ocean, we predict the probability that a juvenile salmon is actually going to be caught out in the ocean fisheries, either the sport fishery or the commercial fishery, as an age 2 or 3 or 4-year-old fish. And we also predict the probability of whether or not juvenile salmon will return to spawn in the San Joaquin River or Central Valley, whether it be an age 2, 3, or 4-year-old salmon. And we do this primarily as a function of ocean conditions, primarily upwelling, which drives trophic levels upon which salmon abundance is dependent upon in the ocean. Now, when the salmon come from the ocean and return inland to spawn, we need to identify whether or not they're going to home to the San Joaquin or they're going to stray to the Sacramento. And as a function of South Delta inflow, as well as Delta exports, we saw some idea of this in the earlier particle tracking model and results. The salmon needs some way to orient to and home in on the San Joaquin. So we do this as a function of South Delta inflow and Delta exports. In conjunction with the homing module, because we know that we have stray fish from out-of-basin hatcheries entering the San Joaquin and going up into each of these individual tributaries to spawn, and we also account for adult production straying into the San Joaquin as a function of numbers of fish that are produced and released from Sac Basin hatcheries, McCollum Hatchery up in here, and the Merced River Hatchery.
Dean, is the strain, does it have any advantage as far as genetic diversity, or do you consider a strain in all cases to be not good?
Depends on what your objective is. We have colonizers that come from the Sac Basin and come to the San Joaquin, so they bring in genetic contribution, if you will. However, if the goal is to see what, for instance, a Merced fish might produce, you know, quote unquote evolve to, if only Merced River fish were allowed to produce in the Merced, then having fish from outside the basin could be detrimental.
So what
So
do
there's
you
like
want?
kind of two schools of thought there.
So what do you want?
What do we want?
Yeah.
Some of each.
Okay. So it's not all bad.
Not all bad.
Okay. Thank you.
Okay, spawning module, this actually closes the loop. So once we calculate how many adult spawners are going to enter the San Joaquin, whether they be of natural origin, produced in the San Joaquin, or whether they be from the Sacramento Basin and coming into the San Joaquin by strays, we partition them, by reach and date up into, I'll use the Stanislaus by way of example, up into the various spawning reaches based upon flow and water temperature approximately 3 weeks earlier. And then the last module, because we do have a hatchery in the San Joaquin River Basin, is to estimate how many salmon the hatchery is going to take or receive on an annual basis based upon the number of fish that spawn in the inland environment. There's a good relationship that says if you have X amount of fish spawning in the inland environment, then we'll have Y number of fish come to the hatchery. And once we know that, then we know how many females we're going to have, how many eggs we're going to get, how many juveniles we're going to produce, and then how many juvenile salmon we're going to release back into the San Joaquin River Basin watershed.
Dean, where does the, I was glad to see it in your matrix there, but where does carrying capacity come? I would assume, you can correct me if I'm wrong, but I would assume carrying capacity doesn't have much to do with adult fish, but it has to do with food availability for smolts that are released from the hatchery in combination with wild fish. Does that have any relevance as to the number of fish that you take around the system, or how do you balance all that from a carrying capacity standpoint?
Well, that's certainly a broad question. You can actually have carrying capacity at every life stage level. You can have it at the adult level. By way of example, you could have